Welcome to the Unit 3, Section 5 video on applications of linear functions. Many real-world scenarios can be modeled by a linear equation. Recall the slope-intercept form of a linear function, y equals mx plus b, where m is our slope and b is our y-intercept. To create a model, read the word problem to determine the slope and the y-intercept. The slope will be referred to as some rate of change. The y-intercept will be referred to as some flat phi or starting value. So our slope m is going to be some sort of rate of change, and our y-intercept will be either a flat phi or starting value, depending on the type of situation that you're encountering. You can interpret the x variable and the y variable by looking at the units of the slope, or the rate of the change. The units in the numerator indicate the y variable, and the units in the denominator indicate the x variable, because we have rise over run, change in y over change in x. Depending on what is being asked, you may have to solve for x or y. So to solve a real-world linear problem, identify what x and y variables represent, identify the values for slope and the y-intercept, create a linear equation using the slope and the y-intercept, substitute a value for x or y and solve for the other, and then using a sentence, express the final answer with units within the context of the problem. So in example 1, Molly earns $8 an hour at her part-time job. She works 4 hours a day, 5 days a week. How much money will Molly earn after working for 4 weeks? So let's let x be the number of hours worked. That is our independent variable. Let's let y be the amount of money earned. That is our dependent variable, because how much money she earns depends on the number of hours she works. So our rate of change is going to be $8 an hour. That is the rate at which she makes money, is at $8 per hour. And that does kind of key us into what y and x are, right? The money earned is dollars, and the hours worked is, of course, hours. Our starting value is $0. If she doesn't work at all, she starts with no money. Our known variable is x here, because we know how much time she is working. She's working 4 hours a day, 5 days a week, and we want to know how much she'll earn after working for 4 weeks. So you can use some dimensional analysis to determine how many hours she will work over the 4 weeks. So 4 hours a day, 5 days a week, 4 weeks, that gives us 80 hours in total. So we take our slope-intercept form, and we're going to plug in 8 for our slope and 0 for our y-intercept, because that is our rate of change and our starting value. And the known variable is x, so we can plug that in as well. So we have 8 times 80, which gives us 640 for y, and that is the amount of money that she will have earned after 4 weeks, $640. During May of 1990, Southwest Missouri received 30 inches of rain. The water level of a flooded river dropped by 3 inches per hour after cresting at 3 feet above flood stage. How many hours after cresting will it take for the river to return to fall below flood stage? So let x be the number of hours after cresting, and let's let y be the river level, because our rate of change is we are going down 3 inches per hour. So in this case, it's going to be negative because our river is falling. Our starting value is 3 feet, okay? Because we ended up 3 feet above flood stage. So we convert that to inches using dimensional analysis, and we find that we are 36 inches above flood stage to begin. Our known variable is 0 inches. We want to see how long it takes to get to below flood stage, with flood stage in this case being at 0 inches. So we take our slope-intercept form, we plug in our rate and our starting value, and then we plug in our known variable, which is our y. Now we can solve this for x. Subtract 36 from each side and divide each side by -3, and we get x equals 12. So it will take 12 hours for the river to fall below flood stage. Sometimes domain and range are restricted to a set of points. We've talked about this before. Quantities such as a number of people can only be whole numbers. When this happens, the graph is not actually connected because every point in the line is not a solution. However, you may see these graphs shown connected to indicate that the linear pattern or trend continues. So a real-world situation and corresponding graph are going to be given. Determine the reasonable domain and range for each scenario. Sue rents a manicure station in a salon and pays the salon owner $5.50 for each manicure she gives. The amount Sue pays each day is given by f of x equals $5.50 times x, where x is the number of manicures. So here is a graph of the manicures against the rental payment. Okay, so now we are going to determine what a reasonable domain and range are. Well, remember, this is a service that she is providing, and for each manicure, she has to pay $5.50. She can't give half a manicure and pay half of the amount. So here we have discrete points plotted on the graph, but we have a line through those discrete points to show you that the trend will continue upward as she continues to give more manicures. So in this case, the domain is 0, 1, 2, 3, and then you can indicate it goes on forever using 3 dots. And our range is 0, 550, 11, 1650, and so on. The Sandia Peak Tramway in Albuquerque, New Mexico travels about 4,500 meters to the peak. Its speed is 300 meters per minute. The tram's distance in meters from the top of the peak after X minutes is given by this function, which is graphed here. And so we have a graph of the function, and you can see a few points are plotted here so that we could graph the function. But in this case, we do have to pass all those distances from the peak on the way to the next distance from the peak. You can't just skip over, say, 3,500 feet, or I should say meters in this case, and go to 3,000 meters as you're descending down. You just can't skip going past 3,500 meters. At some point between 4,000 meters and 3,000 meters, you are at 3,500 meters. So this is continuous, which means our domain is from 0 to 15, and our range is from 0 to 4,500. And you can read that from the graph here. Keep in mind that domain and range can also be limited by physical measurements. For example, time must be positive because you cannot go backwards in time. Be sure to think about what is being measured and what values cannot physically occur.
Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you. And if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.